So good morning. We can start this lecture. We will speak of the final line in our syllabus for this week. And this is integral curves of vector fields and local flow. But I just recapitulate what we learned. We had last times we have 4 definitions of a vector at P on M. So we have a manifold somewhere here, point P, and symbolically some vector at this point. And we learned that how to define this concept, that it is not completely easy, but not complicated thing to define it. And we had 4 independent definitions. More or less 2 of them were quite different. One of them was based on the concept of tangent curves. Second one was based on the concept of derivations of algebra of functions. And then the third was that a differential operator with constant coefficient. The last one was the definition of the 19th century that vector at point P is a set of numbers connected with coordinates in the vicinity of this point. And if you change the coordinates, the set of numbers changes in some concrete way. And all these definitions are equivalent. One can prove that from any one, you can prove any other one. So it is useful to know about all these definitions and to use always the concept of vector which is appropriate to your problem. We will see it already today. Then we went to the concept of vector field. And by the way, the most practical way for working with vector concerning the notations and what is a basis of vectors is this, the second one. Then vector is a derivation of algebra of functions. From this concept, we came to basis of vector in tangent space. This is a basis. I explained it last times, in which sense. And when we came to vector fields, we just try to understand that in coordinates, vector field can be written in this way. That just put away this evaluation at P, because it is in this way of expressing vector field is at the coordinate patch. Here we have coordinates. So here in this part of our manifold, we can use this expression. And also we derived what happens on the overlap if we have O primed with primed coordinates. So here, that it should be the same expression primed. And because we know to recalculate the basis, it is an easy problem to relate these 2 objects. I don't want to go to these details because it was last time. Now I will introduce a new concept today, which is called integral line, integral curve. Important concept. And on this concept, we will base another important concept, which is called flow of this vector field. So imagine, like here, that we have a vector field, and here is vector at point P. They are at each position on the manifold you have a vector, because we have a vector field. Yes? So now, remember that the first definition of vector was that this vector is an equivalence class of curves which are mutually tangent in this point. Yes? So we can write that this Vp as equivalence class of gamma. And by the way, I forgot to use much more frequent notations. This is general notation for any equivalence class, for any in any mathematical situation when you have equivalence classes. So this is completely standard. But in the case of vectors, it is usually denoted like that, gamma dot. Gamma dot is equivalence class. Yes, so this is specific notation in differential geometry for curves that the curve dot means it is not some doing of some derivative. It is a symbol for equivalence class of gamma. So a vector in this presentation. So now imagine that we have vector here. This vector is necessarily some equivalence class because this is the definition. So we can take any representative from this equivalence class, and we can go along this representative parametric distance epsilon. Yes, from some 0 to epsilon. Here is 0, and here somewhere is epsilon. Remember that all particular representatives of this class are identical to this up to epsilon accuracy. Yes, so it is a well-defined concept to go along any representative epsilon because it doesn't depend on a representative. So then we finish somewhere here. This is the first step, that go along this epsilon. And then the second step, repeat the procedure. Because here you find another vector, because in each point you have a vector, because we have a vector field. So here you have another vector. This another vector is, again, equivalence class of some curves. Take any one and go epsilon. And then repeat, and from these epsilons, you obtain some curve. Of course, there is some analytical thing to prove that it has a concrete limit when epsilon goes to 0 and so on. But the idea is clear, I think. So by this idea, from each point, because at each point you have a vector from this vector field, you can start at each point and start a new integral line, integral curve. Integral curve is such curve. And by the way, you can also go backwards. We will show that how you can compute it really. Really, it is not done like that, although you can do this procedure by computer and find integral curve. Yes, it is clear that it is possible for some epsilon practically small and so on. But we invent some differential equation to compute it, actually. This is just the idea. And what is the differential equation for finding integral curves? So if our vector field with respect to coordinate system x here somewhere will be the part of the integral curve. It can go through several coordinate domains, but just in this domain, this is our expression of our vector field. And now, what should be the property of this curve? The property is that when the curve is done already, here is our gamma, to be found. At each point, this gamma has this tangent vector, this gamma dot, and this tangent vector should be identical with the vector from the vector field. Yes? So, in short, this is our equation for finding our gamma. So this is some kind of equation from which we want to compute the curve itself. We do not know the curve in the equation, we know just it's a tangent vector to the curve at each point. Now, just write, this is if this will be in coordinates xit, we will do it for xit, not for abstract gamma. Yes, this is abstract equation for finding gamma, but we usually do it in coordinates. So what we really try to find is coordinate expression, coordinate presentation of this curve. And if this is the coordinate presentation, then this equation in coordinates, the left-hand side, is gamma I dot derivative with respect to I. This is from the, which one now? Maybe third or first or second definition of what is vector. That vector is n tuple of numbers times basis. Yes? So here is the n tuple of numbers times basis. Now, what is on the right-hand side? Here it is vi derivative with respect to I. So, because the basis is the same, we have our equation which looks like that. Or, in more detail, with t yes, that to understand that, by the way, here the dot is the time derivative, is the derivative with respect to this parameter. Here the dot is just the symbol. Here it is not time derivative of something. It is just the notation for equivalence class. Here it is real time derivative, real dot, in some differential equation. So, we have a look and see that what we obtained is a system of ordinary differential equations. So there are differential equations there, and it is a system. How many equations, how many indices? And indices are I goes from 1 to n, which is the dimension of the manifold. Yes? It is the number of coordinates. System of n equations, ordinary, because there is just one independent variable, t. They are so-called quasi-linear. That means that the highest derivative is linear in this equation. In this equation, you see that here is the only derivative in this equation, which is the highest because of that, and the highest derivative is the first derivative. And it is linear. It is just xi and not square or something like that. Here is zero derivative inside the v, so it could be complicated. It depends on the vector field. Yes, but the highest derivative is just linear. So it is not the simplest possible equation, but still not very complicated in this sense. And there is no t inside. I don't remember. There is some class of equations, how they are called. something like homogeneous, but not completely, that there is no t explicitly here. Did you have some classification that there is some, you can find it in the book, yes? It is not important. Something that no t explicitly. Because the more complicated thing will be that t is, of course, inside axis, but maybe possibly explicitly, and it is more complicated. That it would mean that vector field depends on time. Yes, our vector field doesn't depend. It is still the same vector field. So let's compute some example. And from this example, we will see that in principle, you see that this system of equations is written in any coordinates. Yes? So you can use any coordinates and write down a system of equations and try to solve them and find these integral curves. But the choice of concrete coordinates can be reflected whether these equations will be easy or hard. Yes. Now let's have example. So our manifold will be just R2 with coordinates x, y, standard Euclidean plane. And let's have a vector field minus y derivative with respect to x plus x derivative with respect to y. This is very interesting vector field, which we'll meet frequently in the future, because it has some meaning, it does something. We will see what it does actually from the picture we will obtain. So this is component Vx as a function of xy, and this is component Vy as a function of xy, or V1 and V2, yes? Vx, Vy in other notation is V1 and V2. And both of them can be functions of all coordinates, that means x and y. So now we want to write down this system of equations for this V. So this system of equations always has all coordinates dotted at the left-hand side. So we can start with this, because all our coordinates are x and y, and put here Vx, which is minus y, and Vy, which is plus x. So we have our system of equations for finding integral curves of our vector field. These are quite simple equations. They are not very complicated, but still they are well, here are both coordinates, here are also both coordinates, yes, so there is some interaction, so to speak. They are not independent, these equations. We already met this equation on theoretical mechanics, and maybe you also met it somewhere else, so it is not a problem to solve it. And if you do the solution, for example, by adding another dot to everything, that dot this equation, and they decouple, because x double dot is y dot, but y dot is x, so you will have x double dot is minus x, yes, just for x, and solve it. It is some sine and cosine. And the same story here, and you will have 4 arbitrary constants put to equations and get 2 arbitrary constants in the equation. And you will see that solution is x0 cosine t plus or minus, check, I don't know it, y0 sine t, and here will be y0 cosine t and x0 sine t. And if here is plus minus, here is minus plus. And this can be written, in order to understand it, This is the solution with two arbitrary constants, which are just x at time 0 and y at time 0. So it can be written in this way, where here we have this cosine t and this plus or minus. It is just 1, but I don't remember. Check whether it is plus or minus. Yes, so I don't remember, but this is either plus or minus. You should check which is good. And from this, we already understand what happens if we have here x and y, and we start somewhere at x0 and y0. So here we see that we can interpret it as a vector which is rotated by this matrix. So at time t, it will be here. So what the curve looks like? The curve itself is something like that. Or the opposite way, I think that it is by sure like that. So one can check what plus or minus produces this way of going along this integral curve. So we see that as a set of points, it is a circle, but it is a curve. That means that at each time we are somewhere. Yes, it is officially curve. And notice, by the way, important feature that the solution exists for any t here. You can take any t, any big T, plus or minus, and still you have a solution. This is not always true. Because this system of differential equations, there is a big theory around this system of differential equations, and with smooth right-hand side, which we assume that these functions are smooth because we have smooth vector field. There is no guarantee that you have solution for any t from the theory of differential equations. What you are guaranteed that there is a solution for some neighborhood of 0. From 0 to epsilon and minus epsilon, solution exists. But there is no guarantee that you have a solution for big T. And here we see that our solution not only exists for small t, but also from any big T, which is, I don't say that exception, but it is not a rule. Sometimes you have problems with t bigger than something. If there is a definition that if your vector field has integral curves which can be extended to any t, it is called complete vector field. There is a definition that complete vector field is such like that the solution exists for any t. Now, we computed it in simple coordinates, in Cartesian coordinates. Now, if we do the same thing in polar coordinates, you can check. I think that I mentioned it on Monday already. We have some formula how to recompute vector field from one coordinate to other coordinates. So when we use this formula, we come to conclusion that this vector field is very easy in polar coordinates. So it should be VR, R phi in general, derivative with respect to R, plus V phi, R phi, derivative with respect to phi. And of course, this can be done only in the patch on this part of xy plane where R phi are good coordinates, which is not the whole plane. Yes? For example, at the beginning, R phi pair is not good coordinates, but because for r equals 0, any phi gives you the same point. So r phi are defect coordinates, so speak that they are not global. They have some points here in which they don't work. They are bad coordinates. So if I say that this field is the same like this field, I mean in points where when both coordinates work. Yes? Notice that the Cartesian coordinates here are global coordinates. They work in whole plane, but spherical or polar coordinates in the plane don't work in whole plane. Just you should put some points outside. But forgetting about this, we see that our V is this. That means that this is 0 and this is just 1. Very simple components. Now, what does it mean for finding of integral curves? Here should be 0 and here should be 1. So if you compare this system, which is equivalent to this system, you solve the same problem. You see that this is more complicated, although not complicated, but more complicated, like this. Because this is really trivial. You have RT equals R0, the initial value of R, and phi t is phi 0 plus t. So now I will draw a picture in xy plane again. In R phi, it is not very interesting. It is not very informative, but it is informative here that here we have initial point R0, phi 0. So here is R0 and this is phi 0. Yes? And then what happens? R0 is always the same and phi is linear, is this value, the beginning value plus linear addition of t. So the same picture. But if it's true that here is 1, then we see that it goes to the left here. And by the way, this 1 which is here is omega of this motion. In physics terms, it is angular velocity, that's omega, which is unit for this vector field. Well, I draw on this picture just one integral curve, but somehow generic. This is a generic point, and then this is integral curve. But if you draw to this picture several integral curves, you see the picture like that for all circles, including the origin, which is in polar coordinates dangerous to study the origin, but in these coordinates we can study that what happens if our x0, y0 is the origin. Well, we will stay in origin forever. This is a particular case. But the generic case that we rotate around this origin on circles with the same angular velocity for all points. Yes? So if you draw some line, the whole line will be rotated. The complete plane is rotated. So what it adds to our knowledge of the vector field, if we see these integral lines, we practically see the vector field. Because what is vector here? By definition, vector here is like that. Yes? So if you imagine that if you know how integral curves look at your manifold, you practically know that how the vector field looks like. Yes? So it is also very much important for visualization of this vector field. If you want to draw many arrows to your manifold, that how it looks like, just compute integral curves and you will see the arrows inside the curves. Or there will be an exercise for homework that imagine you have a cylinder, something like that, with one coordinate phi in this direction and some coordinate x in this or opposite direction. Yes? So the position on your cylinder is given by coordinate x in this direction and phi in this direction. Then if you will have a vector field, say this one, you can find, this is the exercise, find integral curves of this vector field. So I will not solve it because it will be an offer for homework, very easy, and draw all integral curves or several integral curves to see that what is this vector field, how it looks like at this cylinder. And you will see that there is something like that, yes? You will see by computation. Or you can compute some integral curves on the sphere. Here is North Pole, South Pole, coordinates theta, phi, introduce some simple vector field and try to find integral curves. For example, here, if we have vector field, the basis vector fields, this and this, its integral curves are meridians. They go down. Yes? Because theta grows in this direction. So for these equations for integral curves is theta dot equal 1, phi dot equal 0. And the solutions is that theta is something like here, but for theta, and this is for phi. So constant phi, the solution, and linear theta, it is meridian. Uniform motion along meridian. And for this, it is opposite, it is that curve. Yes? So you can officially solve these equations, and you will see. So I finish with how to find integral curves. You see that always when you want to find the integral curves, write the corresponding set of equations, which is a system of differential equations and so on. Solve it with initial values, and then you will see what it does. Now, one consequence of the fact that we have the concept of integral curves is that we also have something called a flow, extremely important concept for us. We will base on the concept of flow the concept of Lie derivative in chapter 4. So just imagine that we have a manifold with a vector field. So for each point here, we can construct integral curve, which starts at this P. Yes. And now introduce a mapping, not just one mapping, but one parameter family of mappings from M to M that start with P, go to phi t of P, which by definition is that here you are in the beginning, and here is phi t of P, which means that flow along your integral line, and when you come to time t, stop, and this is the image of your mapping. So the starting point is any point on the manifold, and the image point is the point to which you come when you go time t along the integral curve. The integral curve is unique, So you can go from time 0 to time t and then stop and sit at this point. Is it clear that what this map does? That here is any point. Here is integral curve such, this is gamma t, with the property that gamma 0 equal p. So then gamma at t is phi t of p, by definition. And this is done for any point from the manifold M. Any point can be treated as starting point of some integral curve. So for any point, this mapping is well defined. Well, there could be a problem for big T, as I already mentioned, that if your vector field is not complete, that this flow doesn't exist for too big T. Yes? Therefore, it is usually told that the vector field, what guarantees is so-called local flow, which is a little bit tricky definition. What is exactly is something like that for small epsilons, but not precisely the same thing. So the existence of local flow is guaranteed by theory of differential equations of this type, but often we have also flow which is not local but global flow for any t. Yes, so, for example, what this flow does for our vector field. Just repeat the picture, that the flow, what flow does is shown in this picture. That our manifold is now this plane of the green board, and what points do? They flow along these lines. So, for example, this domain with respect to this flow will be here in some time t. Yes? So this completely flows along these lines and comes here in time t. So the flow in this case is rotation of the plane. Another example, v derivative with respect to x in the same plane. What are the integral curves? X dot is 1, y dot is 0, because there is no y. So xt is x0 plus t, yt is y0, yes, from these equations. Now, what is the flow? That point which has coordinates x, y, goes to point with coordinates x plus t and y. It is usual not to write these zeros, yes, here. But this x, y is actually x0 and y0. That at time 0, we are in x, y. When we will be at times t, x plus t and y. This flow in coordinates is in r phi, goes by this flow to r phi plus t, which is just rotation. And what it is here, what kind of transformation we get, what this plane does, or all plane points, what they do if they are acted with this flow. They shift right, exactly. Yes, so any point goes in t to the right. So we also, when we draw the picture for this flow or for this vector, for this integral curve, we see the vector field. So the vector field is just this one. That means something like that at each point. But now we already see that in terms of these flows, we can write down very interesting mappings in our situations in physics. Rotations, translations can be described like flows. Yes, we see already. And many others, of course. So the concept of flow is extremely important for very usual physical situations and mathematical situations. We are now in which chapter? In chapter 2, yes? In chapter 3, we will have some progress in the way that we will discuss what the mappings of manifolds do with mappings of tensors on manifolds. We do not know yet what are tensors on manifolds, but it will be more or less done today. So chapter 3 is something that from mappings of manifolds, you have automatically mappings of some tensors. And then knowing this, how it happens, we can come back to this flow and to define one very interesting way of differentiating of tensors, so-called Lie derivative, which is extremely important. So I think that Lie derivative should be by sure in the first semester of any differential geometry. It is so important and so easy. It is not a complicated thing, but very useful. That it measures something like how much tensors change if you do this flow of your manifold. Yes, something like that. Okay, so now we finished this week already, and we have still quite a lot of time. So we will already start the next week, which is tensor fields on manifolds. Tensor fields. We already know what are tensors in linear algebra. We know what are vectors on manifold. Yes, so there is a not very complicated way to understand what are tensors on manifold, because we spent complete first week with tensors in linear algebra, so we are already well prepared for this step. But still there are some details which are important to understanding what are tensor fields. And so what we already know, well, I will write the title. Yes, tensor fields on M. This is the whole week. And we know already what? What is a vector at P on M, and also what is a vector field on M. But still vector. And we want to go to tensor at point P and tensor field on manifold. So at an idea, it is quite already simple to define what are all tensors. In particular, we know what is a covector with respect to linear algebra starting from some L. That covector is a mapping that the grinder, here goes V, and here is alpha, and here is something, a real number. It's some mapping, covector, yes? So, covector at point P now, or covector at P, what should be? What is a vector? Element of TPM. Now, on manifold already, yes? This is a vector at point P. It is an element of this vector space. We discovered that there is a vector space, tangent space at point P on a manifold. And elements of this vector space are called vectors on manifold. So what are covectors? Linear mappings from this particular vector space to R. Yes, this is our L from the first week. Yes. So what is the vector space of covectors? It is the dual space to this one. So this alpha now is from the dual space of tangent space at point P, by the logic of the first week. That we did nothing more than find a particular L from the first week on manifold. Yes? What we don't know yet, how some nice basis can be defined here. And what is nice? We know basis in TPM. This is this one. And we want to find some ij such that this should be delta ji. That means we want to find dual basis. So we already formally know what is a covector, but we cannot very much work with it because we didn't discover what is a dual basis. We know its property, but we don't know how to realize it. This basis we already know how to realize, yes? They are these partial derivatives, funny. And what are tensors? Multilinear maps from several pieces of TPM and several pieces of TPM star. So in principle it is clear what is a tensor at point P, but we still lack nice formalism for it. And we will describe it. But in order to do that, it is funny that it is better to go to tensor fields and then go back a little bit. So we want to add something to the concept of vector fields, namely that vector fields can be multiplied by functions. This is a new thing which I think that I didn't mention last time, that if you have V and if you have W, you can define this concept, that linear combination of vector fields with when the coefficients of combinations are functions, not just real numbers. So if you have a vector space over R, as we did in the first week, and also in the concept of vector at one point, this was standard vector space when vectors can be linearly combined with over real numbers. It can be also done complex numbers and so on, but real numbers. Now, it makes sense to make linear combination of vector fields over not real numbers, but over functions. Smooth functions. Yes. And smooth functions comprise an associative algebra, which is much bigger than real numbers. Constant functions can be identified with real numbers, but they are also non-constant functions. So, so to speak, it is much richer object than just R. R is a field, and this is an algebra. Yes, this is another object, another algebraic object. So what makes sense to do here is make linear combinations with coefficients from some algebra, namely algebra of functions. And if this is possible, the resulting object is not called linear space, but module. Yes. In a sense, it is something like generalization of vector space. And you have appendix 4 in the book, which is useful to read and to learn that module is a simple thing for us. So you can introduce formally that you have some algebra, and module is something when you can do linear combinations over this algebra. And now, why it is possible here? There is some, let's say, some science over this. You can read this small science in Appendix 4. But now, from practical point of view, why this makes sense? Because what we can do in a single point, if here is Vp and W at P, then you can make linear combination over R. Yes? But this V is also here as Vq. And you can also do linear combinations over R. And this R could be different than this R. Then if you do all vectors and you do linear combination over R for all vectors, and these R's are independent, that means that this is different R in different place. And what does it mean that you have R's in any point? It is a function. Yes? So you introduce some function which collects all these constant coefficients in all points, and altogether this function gives you constants at each point. But this constant could be different. And maybe I also forget to say that here we have tangent space, important thing. Although not very important for us now, but important in principle, that imagine 2 points, P and Q, and imagine the tangent spaces and this at this point. So here, this is a linear space, n-dimensional linear space. Here, the same, yes, n-dimensional linear space. So they are isomorphic. But there is no canonical isomorphism between vectors here and vectors here. So you cannot, at the level of manifold, make linear combination from one vector here and another vector here. It makes no sense. It is not defined. And it is important thing to notice, because in physics it is sometimes done. For example, you have system of particles. Here is one particle, and here it has some momentum, yes, some p. Here is another particle, it has also some momentum. And there is a concept that the total momentum of the system, just add these vectors. But here you add vectors sitting at different points. And this is not possible on general manifold. And on general manifold, each tangent space is a space which has nothing to do with other vector space. This vector space and this vector space are completely independent, and you cannot make linear combinations from between vectors from various points. It is quite clear if you imagine that you have two vectors on the sphere, yes? And now you want to combine them, you see that after some thinking that is not possible. There is no clever way to do it, that what is the resulting vector of summation of two vectors at the sphere. It makes no sense. So why? In the first year of physics, they told us that it makes sense to make a total momentum of the system, or total angular momentum also, because it is done in a very special manifold, namely Euclidean space, and in Euclidean space it is possible. And it is rather big science, well, little bit big science, that why it is possible. Yes, that what is the property of the Euclidean space? What makes it possible to linearly combine vectors in various points? And the answer is that there is a structure called linear connection in chapter 15, next year, not this year for us. And linear connection is the structure which makes it possible. Linear connection with zero curvature, by the way, rather very specific linear connection from Euclidean space, which makes it possible to linearly combine vectors in various points. But for us, it is simply forbidden in general, that there are some possibilities, some very particular manifolds, okay, nice to hear, but in general, the rule is that it is not possible. Yes? Okay, so now come back. This was like footnote to the lecture, somewhere here. And now come back that I try to explain that why this makes sense. That you have vectors in all points, one vector, another vector in any point, and you can make a linear combination at any point, but this means that you can make linear combination with any constant, and any constant at each point means a function. So making this, it is the same thing like make linear combinations with various functions pointwise. Well, if this is not clear, but think over that it should be clear, it is even better argument than the argument through coordinates, but in coordinate notation, our vector field is this, and the second one is this. So, what is a vector field? It is a linear differential operator with non-constant coefficients, in this sense. Yes? First order differential equation with functions as coefficients. So, and it is clear that if any vector field is a linear differential operator with non-constant coefficients, then if we do this object, we have still a linear differential operator with non-constant coefficients, so it makes sense. Yes? Not only with constants. Why just constants? Functions are possible here. But I really recommend you, I hope that this is completely clear idea, but it is also recommended to think this idea that what is possible for vectors in individual, at individual positions, and then what it says for vector field, that here can be smooth function. And that's why all vector fields, which are, by the way, vector fields are what? They are something like vectors, but at each point. You remember that in linear algebra, vectors are this type of tensors, 1, 0 type of tensor. So vector fields at manifold can be denoted like that they are tensor fields of type 1, 0 on manifold. Yes? We didn't introduce TPQ still, but this is just the first tensor field, that vector field. And because vector fields are so important among all tensors, they deserve special notation. They want it, they claim that they are special and they deserve special notation. So mathematicians gave them special notations, and these special notations is like that. They're not just a part of tensors, but specific object. It is Gothic X in tech. And now we want to go to covector fields. Yes. And then to tensors. So what is a covector in linear algebra? Or, well, in linear algebra, so alpha from the space of covectors, the dual space, is a mapping L to R. So what is a covector at point P? Now, it is a mapping from TP M to R linear. This is a covector at P, by definition. That just take L to be the tangent space, and you have what is a covector at point P. This is general in linear algebra, and now our linear algebra is applied to the tangent space as L, and that's why everything holds from the first week with just putting L to TPN. Now, the dual space, the space of covectors, is this guy, the original space with star, and again, it is usually denoted differently, namely in this way. Rather different notation. It is the same concept. It is called cotangent space at P. So tangent, this is tangent space. And this is the dual of tangent space, which is called cotangent space. And notice that this notation is rather exceptional. Official notation is this, but this is not used. This is used. And what is a tensor? Several copies of tangent space, several copies of cotangent space, going to R. It is just first week linear algebra. What is PQ type tensor at point P? It is a multilinear mapping from here to here. If we know it, what is a tensor in linear algebra, this is automatic. Nothing very much interesting. It starts to be interesting if we want to realize this fact in practice. Yes, but ideologically it should be clear if we understand the first week. That real practice from us needs what is the basis here? This one. Now the question is, and what about here? Sorry, here is this one. And here is question mark that what is the basis in the cotangent space? We do not know. And then, very important thing, simple but important, something similar like this module idea here, that what about tensor fields? In particular, what about covector fields on manifold? That what type of mappings they are actually? Yes, that what should be a covector field? Covector field should be a covector at each point, by definition. Like vector field is vector in each point. So imagine at each point you have this grinder that put me vector and I will give you a number. Yes? So if you put to all grinders vectors, actually you put inside a vector field. We can regard it as this. Yes? That our argument is a vector field because our argument, there are many grinders, so they need many vectors. At each point they need one vector. Yes? This is a covector field. Grinder for vectors in each point. So what should you do? What should you put to all these grinders? Vectors at each point. What is it? A vector field. So we can regard the arguments for covector fields that they are vector fields, not vectors, individual. Yes? So if alpha is a covector field on M, you put vector fields inside. And what is the result when you put all these grinders vector field, that vectors? At each point you get a number. But a number at each point is a function. Yes, it is not a number. So a covector field is a mapping. Vector fields go to functions. Yes, so we can write it that a covector field is vector fields to functions. Do you remember what is a tensor of type 0, 0 in linear algebra? No. And what in simple language? Well, this is number. This is just R. Now, what should be T00 on M? Tensor of type 00 at each point. But tensor of type 00 is a number, so number at each point, that is a function. So here, it is just tensor, it is tensor field of type 00. Here is tensor field of type 10. So covector field can be regarded either in this notation or this notation that vector fields are type 10 tensor fields, and functions are just type 00 tensor fields. And now the crucial point is that what about this linearity? That what is here? It is covector in each point. What is a covector? It is a linear mapping over R. Yes, linearity is over R. But here, it is at each point, it should be linear. And these coefficients of linearity, which we do, this lambda 1, lambda 2, or something like that, are numbers at each point, but not necessarily the same numbers, again. So, this linearity in this slot should be that if you have two vector fields, or vector field and another vector field, once again, it should be f allowed to be here, function. And it should be linear in this sense. So, at the level of fields, we need not just linearity over R, but we need linearity over functions. That means it is the linearity in the sense of module. Yes? That's why in differential geometry we speak of two types of linearity. The simpler one is R-linearity, and the stronger one is FM linear. So some objects can be R-linear and other objects can be FM linear. If it is FM linear, it is also R-linear, because for constant functions you have just constants. But if it is just R-linear, it is not necessarily FM linear. So, and what do we need to define a covector field? It is a mapping from vector fields to functions, which is FM linear. Yes? So, it is like in linear algebra in the first week, but instead of numbers, we have functions now. Now, and what should be, for example, tensor field of type 1, 1? It should be some t acting or eating vector and covector. Yes. With the result in functions, not numbers, from the same logic. And it should be bilinear, linear in vector and covector, but of the type FM linear, yes, the stronger linearity. Bilinear because we have two arguments. And this is extremely important. So if you don't understand it yet, think it over until you will understand that we need FM linearity here in fields. Okay, and now what should be the tensor field of any type? Put several vectors, several covectors, obtain a number, not number, sorry, a function, and it should be multilinear, FM multilinear. So the only change from the linear algebra of first week to now application of this linear algebra to tensor fields is that it is very similar up to the moment that the result is not a number but a function, and the linearity is in the FM sense, not in the R sense. That only then we have the concept that at each point we obtain a tensor in the sense of the first week. Yes? When we apply FM instead of R, only then we will have pointwise the situation from the first week. And that is our aim, that to repeat the first week for all points of the manifold. Yes? Okay, so we have already knowledge what is a tensor field, okay, but still we do not have the basis, useful basis for covectors, and that's why useful basis for tensors. Yes, but because you remember that in linear algebra, on L we have some basis, and here we have dual basis, and that's why we have, for example, for T11 tensors, we have basis EI tensor product EJ. Yes? So now we are in a position that we know already what is this on the tangent space, that on manifold. This we do not know, so we do not know the basis for any tensors which need this dual basis. That means this dual basis comes for lower indices. We just we are already able to write down tensors with just upper indices, but not general tensors, because we do not know this. Okay, it is surprisingly simple to find it. We now introduce such a thing that imagine we have a function from Fm, and we introduce something called df, which is called gradient of f, and it is from T01M. So it is a covector field. This f itself, remember that f is a scalar field, that it is a function. And now there is some magic d, which when applied on function will give you a covector field. So it makes from T00 T01 tensor field. Yes? Maybe you heard about gradient many times, but remember that whenever you heard about gradient, it was a vector field. Now we introduce gradient as a covector field, and only after that we can introduce the well-known gradient as a vector field. So now it is important thing that it is a covector field. Not a vector field. Vector field will be obtained from it by racing of indices, but without racing of indices directly, it is a naturally covector field. So this is just a claim that it is a covector field. If something is a covector field, we see it here, it is not here already, that what is a covector field? It is a mapping vector fields go to functions. Yes? And it is FM linear. So if we claim that this is a covector field, we should put inside a vector field and obtain some function. And so it should go on by some prescription, which gives you a function, and then you should check that it is FM linear in this V. Yes? So the definition of this is that it is V applied on F. Very simple definition. Remember that we already defined this object, that vector fields are first order differential operators acting on functions with result functions. So this is really a function. If f is a function, then Vf is also a function. So, okay, the first part of definition is successful, that we have a rule that if we insert vector field to something, this something, we obtain a function. But the second point is it Fm linear? That what about putting this guy as an argument with some other function, of course, that f, some general function psi. Psi is a function again. So what we get? We get V plus psi W, this vector field, acting on f. We already discussed this guy today, that what is it? It is just V acting on f plus psi W acting on f. More or less by the definition. Yes? So we know that this is the fact from today. It was somewhere in this part of the blackboard, I remember. But what is this? By this definition, backward. It is df on V. And what is this? It is df on W. So what we get altogether, we obtained that this prescription really is Fm linear in V. Okay, so what we obtained? We obtained a prescription which enables us to create covector fields. Not general covector fields, but covector fields of this type. For any function f, we can construct gradient of this f, and it is a covector field. And what about these guys? xi are functions. Not on the whole manifold, but just here. But here they are functions. So if we restrict that we will work in this coordinate patch, xi are functions. Coordinates are functions, yes? So this makes sense. And what about this result? So this is our f and this is our v. Very special objects we put. As function, we put coordinate function. As vector field, we put basis vector fields. So what we obtain from this definition? Apply this v on the function f. So apply this vector field on the function xi. Put it differently, differentiate xi with respect to xj. Yes? And what is it? What is it? Delta. And what it means now? It has very, very important meaning now. We computed something quite easily from the definition, and we obtained something which is very valuable for us. It is some statement about this guy. What statement? That this is a dual basis. Yes? With respect. Very important statement. I put it in this way. Very important is basis and even dual basis. So what does it mean? It is a basis, first of all. So any covector field can be decomposed with respect to this basis with some coefficients, which are functions, which are called components. And how they are computed? Go back to linear algebra. and it is alpha on this. Alpha is a mapping vector fields to numbers, or to functions, sorry. So this is some function, call it alpha I. And then we know all that from the first week, that components of any tensor are computing that put bases as arguments to your tensor, and you obtain components. So here, by standard method, we obtain that if this is a basis, these components are computed like that. And we know already, so it is a basis. It is for us already a success that we finally have a basis. And it is even a dual basis. So it is the nicest basis possible when derivative with respect to I is a basis of Tm. So now we know that this vector space has a nice basis, this. And the dual has a nice basis dxi on P. But we don't want to work in individual points. We want basis for fields. So any vector field can be written like that, and any covector field can be written in this way. And if we put now to alpha v, we can insert this for v and this for alpha. I will do it because it is now important. Alpha I x dxi vjx derivative with respect to j. Now we use Fm linearity of both sides. That means this can go out and this can go out. It is Fm linearity because they are functions, not just R-linearity. So we will have alpha I x vjx, and what remains? dxi derivative with respect to j. This is dual basis, so it is delta ij. So the result is alpha I x vi x. It is I. So it is exactly like linear algebra in the first week, but for fields now. So notice that these two bases are dual at each point. So we have basis vector fields which have the property that evaluated at any point, they are mutually dual. They are fields dual in each point P. Yes? So this property is that, remember that there are fields here, so the result should be a function. Now the function is delta ij. It is a constant function, very specific case. It should be from Fm, not from R. Yes? These bases are called coordinate bases. So whenever we have coordinates, we have some preferred bases. If you have coordinates, you have this and this basis, and they are called coordinate bases. This is coordinate basis for vectors. This is coordinate basis for covectors. But if they are dependent, that they are not independent, yes? They are both this and this from the same coordinates. And if you change coordinates, you can check. You will have primed and primed here. Yes? For example, what is here? It should be gradient of this primed x as a function of unprimed, of this. This is our f now. Yes? So if this is our f, well, first, we know that arbitrary covector field can be decomposed with respect to the basis like that. Now, for df, that means that it is also the case. Yes. Now, what is this guy here? By definition, here is still the definition. It is df evaluated at this basis. Now, there is already not the definition, but remember the definition of df is that apply this vector to this function. Yes. So, we can go on. Very important fact that df is computed like that. Do you know some object from your study of mathematics, maybe in first or second year, that what is computed also in this way? There is some object which is called differently, and it is computed in this way, in mathematical analysis. Total differential, exactly. So if you remember what is a total differential, it looks exactly like this way. There is some different interpretation when you have total differential. Yes, so it is sometimes useful to interpret it that these are some changes, small changes of coordinates, something like that. Here it is not this interpretation. There it is basis of covector fields, nothing more, yes? And this is gradient of coordinate. But sometimes it is useful to go to this interpretation, like changes of coordinates, but you should motivate it. That is it true that we can have a look like changes of coordinates? Yes, if you think it over properly. But we do not do it here, yes? So now we already know what is the basis for arbitrary tensor fields. For example, T11, yes, here. What should be the basis for arbitrary tensor fields of type T11? If we know this and this. From the first week, we know that it should be this basis. Yes? And what will be the most general object? Ti j x dxi partial j. This is the most general tensor field of type 1, written in coordinates, at coordinate patch. What about metric tensor, by the way? Metric tensor is 0, 2 tensor on M. So what is it? It is gijx dxi dxj. This is metric tensor at each point of the manifold. It is metric tensor as a field already. So we can now return here. We know already how to compute d of any function. This is our recipe. So this is our function. So it is j applied on this function dxj. And what is this? It is this derivative. It is just in full notation, and it is just Jacobi matrix. Then, just the last question, what happens with this basis? Do you remember the fact from the linear algebra that if vectors are scrambled by some matrix, what do covectors? So what are the scramble matrices for vectors and covectors? How they are related? They're inverse, yes. So if here is J, here should be J to minus 1 matrix, which is, by the way, the matrix of opposite derivation, the differentiations, yes? X primed with respect to, X non-primed with respect to primed. Okay, that's all for today. Thank you.